Hi everyone! So recently, as some of you know, I've been working on a project where I try to start a real startup that's based on this app I'm making for learning languages. And in this process, I ran into a problem where I needed to use dynamic programming to solve it. So I'm going to show you what the problem was and how I solved it. So like I explained in one of my previous videos, on this app I'm developing, which I'm thinking of calling Edit Dojo, people are going to write stuff in different languages and other people are going to fix them or edit them for them. So one person might write, the breakfast I had today was awesome, and someone else might edit this to this, the breakfast I had today was awesome. And the function I was trying to make is the function that shows the difference between these two sentences. So given these two sentences, we want to be able to say that this word has been deleted from the first sentence and also this word, and then these two words have been sort of added to the second sentence. And there are a few different ways of going about it. One is to compare these two sentences word for word. That's what I've done, and that's why you see these two words changed. But another way to do this is to compare these two sentences character by character. So if you take that approach, the UI might look like this instead. So here you can see that instead of showing the whole words being changed, we're only saying, okay, this character O has been deleted, and the same thing with this letter E. So which one is a better approach? Well, I think either one works, but in my opinion, the comparison by word approach is much easier to read. So that's what I'm going to use for English. But the thing is, for languages like Japanese, there's no easy way to split a sentence by words. So I decided to use the comparison by character approach for languages like Japanese. And in this video, I'm going to explain the comparison by character approach because it's much simpler to explain. Anyway, whichever approach you decide to take, this problem actually reduces to another problem called the longest common subsequence problem. I already talked about it in one of my really old videos actually, but let me explain what it is here again. So in the longest common subsequence problem, you're given two strings, for example these two, ABCD and ACDB. You want to be able to find a common subsequence between these two strings that's the longest. So in this particular example, the answer would be this one, ACD. So as you can see, this is a subsequence of the first string. It's ACD right here, and it's a subsequence of the second string as well, ACD right here. And there are usually multiple common subsequences between these two given strings. In this example, another common subsequence would be this one, AB. There's AB right here, and there's AB right here in the second string as well. But in this problem, you want to be able to find the longest one of those common subsequences. And again, in this example, the answer is this one. And sometimes there are multiple answers. There are multiple longest common subsequences. But let's just say that here, we just want to be able to find at least one of them, and it doesn't matter which one we find. Okay, now let me just quickly explain how we can apply this problem to solve the problem that we saw earlier. So let's say that the original text is this one, I am waiting. And let's say that someone else fixed it to this one, I've been waiting. Then what we can do is we can first find the longest common subsequence between these two strings. That would be this one, I space waiting. And then to find which parts of the first string has been deleted, we can compare this string with the longest common subsequence, this one, which is basically the common part of these two strings. And then when you do that, you'll see that this part, just am, has been deleted from the first string because the common string I space waiting is right here, and then what's left is just this part. And then you can do the same thing to the second string to see which parts have been added to the second string. So compare the common string with the second string, and you see that the parts that have been added is this part and this part. And then, you can highlight those parts to get this text. Okay, so that's going to be the idea of my solution. Of course, the first step of going about this solution is to solve the longest common subsequence problem. So let me show you how I would solve that part. Okay, so I'm going to write a function called LCS of these two strings, and this function is going to return the longest common subsequence of these two strings. And I'm going to solve this problem recursively. And one case of this recursive solution is going to be when the given two strings have the same first letter, in this case A right here. And in that case, we'll say whatever the longest common subsequence of these two strings is, it must have A as the first letter. So it's sort of like taking off these two letters and then saying the longest common subsequence of these two strings is going to be A concatenated with the longest common subsequence of these two strings, BCD and CDEB, the rest of the strings. So we can write that as the longest common subsequence of these two strings is going to be A concatenated with the longest common subsequence of the rest of the strings, BCD and CDEB. And this might be actually a little bit hard to get your head around, so I'd recommend playing with a few examples to see why this is actually the case. Anyway, let's go to our next case. That's when the given two strings don't have the same letter at the beginning. We have BCD and then CDEB, for example, in this case. So in this case, we're going to try two things. One is we're going to take off the first letter of the first string, and then we'll ask ourselves, what's the longest common subsequence of the rest of the strings? So CD and CDEB. And then we're going to do the same thing with the second string. Take off the first letter of the second string, and then ask ourselves, what's the longest common subsequence of BCD and DEB? And it turns out, whichever is the longer common subsequence is going to be the longest common subsequence of the given two strings. So we can informally write it as the longest common subsequence of these two strings, BCD and CDEB, is compare these two longest common subsequence, CD and CDEB, and then BCD and DEB. So that's CD and CDEB, or BCD and DEB right here. And then just take the longer one of them. I'll just write it as max. Again, this might be a little bit hard to get your head around, so I'd recommend playing around with a few examples here too. Now, if you implement this function as is, you'll need to create new strings every time we call this function. So for example, if you're given LCS of these two strings, ABCD and ACDEB, we'll need to create these two strings, BCD and CDEB, to call this function recursively. And that's pretty wasteful, but we don't have to do that. Instead of doing that, we're going to pass in two new arguments that are going to specify which letters we're currently examining in these two strings. So instead of saying LCS of ABCD and ACDEB, we'll say LCS of these two strings and then 0, 0. And that's going to mean we're examining this letter right here, which has the index 0, and this letter right here, whose index is also 0. And then when we call this function recursively, instead of generating new strings, we're just going to change the indices. So we'll say LCS of ABCD, ACDEB, and then 1, 1, because now we're examining these two letters, B and then C right here, whose index is both 1. And we can do the same thing for this case as well. Instead of passing BCD and CDEB, the original strings might be ABCD and ACDEB. And then we're passing 1, 1 as we saw earlier. And then instead of creating these two or these four strings, we're just going to change the indices again. So this is going to be like that, max of LCS of the same strings, and then 2, 1, and then LCS of the same strings, and 1, 2. Okay, so let me show you how I would implement this function recursively, and I'm going to show you that using pseudocode. So like we saw earlier, we're going to write a function called LCS of S1, S2, the two strings, and I1, I2, the two indices of the letters that we're examining. And then outside this function, we're going to have to call this function with the two given strings and 0, 0 because we're going to start with the first letters. Anyway, the first thing we're going to do in our main function is we're going to take care of the base case. And that's when I1 is equal to S1's length or I2 is equal to S2's length. And this is sort of like saying what's the longest common subsequence between an empty string with another string. And the answer is an empty string, so we're going to return an empty string from here. And the next case that we need to take care of is when the current letters that we're examining, S1 square brackets I1 and S2 square brackets I2 are the same. If that's the case, we're going to return S1 of the current letter, S1 of I1, it should be I1 here, concatenated with the longest common subsequence of S1, S2, I1 plus 1, and I2 plus 1. And if we haven't returned yet at this point, that means that the current letters that we're examining are different. So in that case, we'll need to find two results, result A and result B. Result A is going to be LCS of S1, S2, I1 plus 1, and I2. And then result B is going to be LCS of S1, S2, I1, and then I2 plus 1. And then we're going to have to compare the lengths of these two strings and then return the longer one. So we can do that with if result A's length is longer than result B's length, then we're going to return result A, and otherwise we're going to return result B. Okay, so this function works, this implementation works, but it turns out it's very, very inefficient. And the reason is because we end up calling, the same function, LCS, with exactly the same arguments over and over again, depending on the strings. So for example, we might call LCS of S1, S2, 2, 3 over and over again, depending on what the strings are. And every time we call this function, we need to recompute what the result is for these particular arguments. And this is where the idea of dynamic programming comes in. Dynamic programming says, why not store the return value of this function with these particular arguments so that we can reuse it? And so that's the idea. Let's see what the code is going to look like. Okay, so this is part of the dynamic programming solution code. And it's pretty much exactly the same as what we saw earlier, except for this additional argument that I added here called memo. This is going to be a two-dimensional array that's going to store the return values of this function, LCS. And so before we call this function, we're going to have to initialize a new two-dimensional array whose size is going to be s1.length by s2.length. And then the result or the return value of LCS of S1, S2, I1, I2 memo is going to be stored right here in this two-dimensional array at the indices I1 and I2. And so, outside of this function, we're going to have to initialize that and then call LCS with S1, S2, actually 0, 0, and then memo. And let's just assume here that every element of this array is going to be initialized to either undefined or null. Okay, and once you have that, after taking care of the base case, we'll say if memo at the indices I1 and I2 is not undefined, that means that we've already seen these particular arguments, I1 and I2, and we've already stored the return value of this function with those arguments in memo at this location. So we're just going to return that by saying return memo square brackets I1 and I2. And what about this case when we haven't returned at this point and when the letters that we're examining are the same? This case right here. In that case, instead of returning the thing that we saw earlier, the first letter concatenated with LCS or the result of the next LCS call, we're going to store that in memo at the location that we saw earlier at I1 and I2, just like that. Memo square brackets I1 and I2 is equal to this thing that we're going to return. And since we just stored the return value of this function with these particular arguments in memo of I1 and I2, instead of computing it again, we're just going to return that, just like that right here. Okay, and to make this function complete, you need to do the same thing basically for the second case, when s1 square brackets I1 is not equal to s2 square brackets I2. So before you return the result, you'll need to store it in memo and then return that instead. Okay, so once you have all of that, this function is going to be complete. But what about the time complexity? Well, just in case you're curious, here it is. Suppose we write s1's length as L and s2's length as M. Then the time complexity of this function is going to be this, assuming that my analysis is correct. It's going to be big O of L times M. And if you're curious why that's the case, I'd recommend watching my old video about the longest common subsequence. And this is actually much better than the naive recursive solution that we saw earlier, which has an exponential time complexity. Okay, so that's the idea of this code, but let me show you if we can actually implement it using JavaScript. Okay, so here's the setup I have here. I have this HTML file, test.html, for showing the test cases. We have a few test cases here. One of them is this one. The original text is ABCD, and the edited text is AFKD. And the longest common subsequence between these two is AD. So our function given these two strings should return AD. So that's the expected result. And the result of our function will come in here after actual result. And our function right now just looks like this. It's just a function that's called LCS. That's going to take two strings, S1 and S2, and returns a string. So if I change this to hello, we should see hello right here. Okay, let's start by implementing the naive recursive approach. I'm gonna create a new function called helper, which we're gonna call recursively. So this helper function is gonna take 4 arguments, the 2 strings, S1 and S2, and then the indices of the letters that we're examining. That should be 0, 0 at the beginning. So let me define the function helper here too. This is going to take S1, S2, and then I1 and I2. And just for testing, let's return hello 2. And make sure that's showing on our HTML file here. And by the way, I'm going to put the end result of my code today at csdojo.io/text, so you can play around with my code yourself too. Anyway, let me implement the rest of the recursive solution. So the base case was when I1 is equal to S1's length, or I2 is equal to S2's length, we should return just an empty string. And then the second case is if S1 square brackets I1, or the current letter that we're examining, is equal to S2 square brackets I2, then we should return S1 I1, that's the current letter that we're examining, concatenate it with helper of S1, S2, I1 plus 1, and then I2 plus 1. And for the last case, I'll say first let result A be equal to helper of S1, S2, I1 plus 1, and then I2. And result B should be helper of S1, S2, I1, and then I2 plus 1. And then whichever is the longer, we're going to return as the result. So I'll say if result A's length is larger than result B's length, then we're going to return result A, and else otherwise return result B. Okay, so this should work. Let's see if it works by going back to the browser. And when I refresh this, actually this takes too long. And the reason is because the naive recursive solution is, very inefficient. So to sort of fix that for now, we have 3 test cases, right? One of them is pretty short, but the other 2 are kind of long. Let me close this window for now. So the 2 test cases that we have here are pretty long, the text. I am waiting for snow, and the breakfast I had today was awesome. So the naive recursive solution is efficient enough for the first case, but not efficient enough for the 2 other cases. So I'm gonna take them out just by changing the code here. And then I'm gonna go back to the browser. And when I open the file again, I see the correct result. Okay, let's now make this code more efficient by using the approach that we saw earlier. So the first thing we want to do in this parent function, LCS, is we want to initialize a new 2-dimensional array called memo, whose size is going to be s1's.length by s2's.length. In JavaScript, there's a neat trick for doing that. So let me just write it here. First, I'm going to write square brackets dot 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 array s1's length. This produces an array of length s1's dot length, whose elements are going to be undefined. And then I'm going to say dot map e arrow and then array s2's length. So with this, we can create a 2-dimensional array whose size is s1's dot length by s2's dot length. After that, we'll just need to pass this memo to this helper function. So let's add memo here, and then also here, and basically everywhere a helper is called. So here, here, and here. So this doesn't change anything algorithm-wise, but let's just make sure that everything still works. And it does. So let's go back to the code editor, and then let's keep going. Okay, the next step is after taking care of the base case, we'll say if memo I1, I2 is not exactly equal to undefined, then we're just going to return that memo of I1 and I2. And then in the first case, when S1 of I1 is equal to S2 of I2, we're going to store this return value in memo of I1 and I2, and then we're going to return that instead. And we're going to do the same thing here too. We're going to first define a new variable called result, and then instead of returning a result A and result B here, I'm going to put it here. So result is equal to result A or result B, and then before we return the result, we're going to put that in memo of I1, I2, and then we're going to return that instead. So this is going to hopefully work. Let's see if it works for this particular test case, and it does. Let's fix test.html so that we can test the other cases too. Hopefully this is going to be fast enough for the other 2 cases too. So let's see if it works here, and it looks like it's working. So in this case, the expected result is I waiting for snow, and the actual result is the same, and it looks like it's working for the third case too. Okay, so what I'm going to do now is I'm going to implement the rest of the algorithm here so that we can actually show the difference between the 2 given sets of text. Okay, so here's what I have now. As you can see, we have, for example, in this example, we have the original text, the edited text, we have the LCS, but we also have the this view where we are showing the original text, but we're also showing which parts of it have been deleted. We show the edited text, and we show which parts have been added in blue text. And the way I did it is, like I explained earlier, I compared the LCS of these 2 strings with the strings. So for the original text, I said, okay, what's the difference between I waiting for snow and I am waiting for snow? And the difference is am. So I highlighted that part in red. And then I basically did the same thing, compared LCS with the edited text. And the difference is this part, verb been. And that part has been highlighted in blue using CSS. Okay, so like I said earlier, I'm going to put all this code in csdojo.io/text so you can check how it works and play around with it. And also, I recently set up a Discord server for this channel, so you should come join us at csdojo.io/d if you haven't yet. And this was, of course, part of my Build a Startup series, which you can find at csdojo.io/start or through a link in the description below. Anyway, thank you as always for watching my videos, and I'll see you guys in the next one.